Welcome everyone to a session on Automata Theory and Computability. This subject is known with different name in different curriculum. Some of the names are formal language and automata theory, finite automata and formal language. But basically they tell the same story. Let us start the session with an introduction. In introduction, we will answer two important questions. The first one is, what is an automata? The term automata is actually a Greek word which means self-acting. An automaton is an abstract self-propelled computing device that follows a predetermined sequence of operations automatically. And throughout the course, we will be designing such computing design, or to be more appropriate, I will make use of the word computing machines. Okay. The next important question is, why to study theory of computation? Theory of computation is mainly concerned with the study of how problems can be solved using algorithms. It is the study of mathematical properties both of the problems and of the algorithms for solving that problem. And it neither depends on the details of today's technology nor the programming language that is used to implement the solution for the given problem. And theory of computation has plenty of applications. Some of the prominent applications are listed here. Development of machine languages. This enables both machine to machine communication as well as person to machine communication. Without them, none of today's applications of computing could exist. Example, network communication protocol, HTML, etc. Then development of modern programming languages. Both the design and the implementation of modern programming languages rely heavily on the theory of context-free languages, which is a major part uh, in the course. Okay? And the compiler is designed entirely on the fundamental concepts of automata theory. In fact, uh, ATC can be said as a prerequisite course for compiler design, which you will be learning in the upcoming or higher semester. Okay. Natural language processing. It is concerned with the interaction between computers and human languages. Automated hardware systems. The application of automata theory and computation is not only restricted to designing the compiler and in the software field, but some of the hardware systems such as parity checkers, vending machines, communication protocols, security devices are designed based on the principle of automata theory and computability. Video games. Many interactive video games are designed based on a large number of non-deterministic finite state machines. Okay, some of the other applications are in uh, in the field of security, artificial intelligence, and graph algorithms, um, which is used in network in the field of networks and algorithms. Languages and string. Okay, these three entities, alphabet, strings, and languages, are the most important concept in the entire in the entire course. Or in other words, I would say uh, the entire course revolves around these three entities: alphabets, strings, and languages, and all these three are interdependent on each other. So let us look into each one of those in detail. Alphabet. We'll start with an alphabet. First, let me define alphabet. An alphabet is a finite set of symbols denoted by sigma. Okay, so it is a set. It is basically a set which consists of symbols. An example would be, okay, a simple alphabet set sigma, which is defined as a set containing four symbols A, B, C, and D. Strings. So how can I define a string? A string is a finite sequence of symbol that is taken from the alphabet set which is defined. Okay. Example, yeah, CABCAD is a valid string on the alphabet set sigma, which consists of A, B, C, and D. So, so this CABCAD is a string which is made with the combination or sequence of the alphabet set given. So any sequence of characters which is made up of the alphabet set is a valid string. Okay, let us see a few more examples. The lowercase in English alphabet, which consists of small letter English alphabets from A to Z. So this is the my alphabet set, and this is a sample example string. Okay, which is a combination of small lowercase English alphabet, and here you can see a special symbol, right? It is called as epsilon. Okay, epsilon is a symbol that is used to represent no combination or no sequence of alphabet, or in other word, it is a string of length 0. Okay, it's an empty string. So empty string is represented using a special symbol called as epsilon. Okay, another example would be binary alphabet, which may consist of 0 and 1, and this is a sample valid string for the given alphabet set. Similarly, I have star alphabet and musical alphabet, and these are the example for the respective alphabet set, okay, or strings of a respective alphabet set. Let us see the various functions that can be performed on strings. Okay, the first one would be length. Length of the string can be calculated or obtained by using this symbol. Okay, so S is the string, and this will give me the length of the string in integers. Okay, for example, string ABB. Now, if I want to find the length of the string, what would be the answer? It consists of 7 characters, right? So the answer would be, the length of the string would be 7. Okay. Very importantly, the length of epsilon is equal to 0. So as I already told, epsilon represent a string of length 0. Frequency. Okay, so this is how I can represent or calculate the frequency of a character present in the string hash C of S. So this basically says, or basically calculate the number of occurrences of the character C in the string S. Okay, with an example we'll get a clear idea. Okay, so this asks, or this determines the number of times the character B occurs in this in this string ABB AAB. So what would be the answer for this? How many times B occurs in this in this string? It is equal to 3, right? Okay. Next one is concatenation. Concatenation of strings S and T is written in this way, or it can be simply written as ST. So where I concatenate S and T. For example, if S is equal to automata and T is equal to theory, then ST gives me automata theory without space, right? And one important property of concatenation is it is associative, right? So if I have 3 strings A, B, C, then A concatenated with BC is equal to AB concatenated with C. Functions on string. Okay, we'll continue with the few more functions. Replications. So what does replication say? So this is how I can define a replication. For each string W and each natural number I, the string W of I is defined as W of I plus 1 is equal to W concatenated with W of I, and W of 0 is equal to epsilon. So basically I'm replicating the string W with I number of times, and if it is equal to 0, then I'm repeating W 0 number of times, which gives me epsilon, right? We'll consider some example. Okay, so A is a string which is replicated thrice. So what do we get? A, right? Similarly, by is replicated twice. By is W, and 2 is the I value. So what do I get? By. And one more, A replicated 0 number of times concatenated with B, which is replicated thrice. Then I get epsilon concatenated with BBB. Reversal. Reverse of a string is defined, or the symbol for the reversal is W of R. Okay, this is how I can define reverse. If the length of W, if the length of string is equal to 0, then reversal is equal to the string itself, which is nothing but epsilon. Okay, and what if the length of W is greater than or equal to 1? Then I can say there exists a character A which belongs to the alphabet set sigma, and there exists U that is uh, that is made up of, that is a sequence of string which is made up of the alphabet set, such that W is equal to UA, where again I repeat, U is the sequence of characters that is created from the alphabet set, and A is the last character of W. Then I can define W reversal is equal to A concatenated with U reversal. Okay, so A is compulsory, as the length of W should be greater than or equal to 1, and U is any sequence of symbols built from the alphabet set. Okay. For example, if I have to take um, name tag, if W is equal to name tag, then the reversal of name tag is gateman, right? Okay. Let me come to languages. Let us define language. A language is a finite or infinite set of string over the finite alphabet set sigma. Okay. So string is derived, or it is string is related with the alphabet set, right? And language is again in turn related with the strings as well as alphabet. So what does it say? Language is a finite or infinite set of strings that is made up of, or made from, the alphabet set sigma. Okay, so let us see an example. So let us consider finite, as the definition say it can have a finite or infinite set of strings. Let us see the finite set. Okay, so this is the way how I can define a language. Okay, L is the language what I'm going to define. It is made up of W, which belongs to alphabet set A and B. So W is a string that is made up of the alphabet set A, B, and as you can see, there is a star which is affixed at the end of this alphabet set, which says strings can be made up of any combination of A and B, okay, including zero combination of A and B, so including epsilon. And on the right side I have the definition for the language. So what does this definition say? String of length 2. So string can be made up of A and any combination of A and B, but the valid string belonging to the language should be of length 2. So what can be the answer for this? Yes. So this is the valid set of strings for the given language: AA, AB, BA, and BB. So I cannot have any further combination which can fulfill the definition of language of length 2, right? And this is an example for finite set. Okay, let us take some infinite set. L, which is equal to again made up of the same alphabet set, and string of even length. Now the even length string is of a combination of A and B is infinite, isn't it? Starting from a string of length 0, so which is epsilon. So this is an answer, or an example for a set of a language of infinite set, starting with the epsilon, then a string of length 2, then followed with a string of length 4, and so on, which goes up to infinity. Okay, techniques for defining languages. So to define, since language is again is a set, I can make use of the concept of set theory in defining a language. Okay, so even number of ways. This is an example how I can define a language L. L is a language which is made up of string W, which is again built from an alphabet set A and B, star represent any combination, and the definition of the language says even number of A's in W. So what can a string contain? String can contain, or a language can contain strings that consist of even number of A's. Okay. Okay. So this is a valid example. Some of the valid strings belonging to the language epsilon, which consists of zero occurrence of A, which is even number, right? B, single B, again it consists of zero occurrence of A, and I'm not bothered about the number of B's as it is not defined in the language. So even this is valid. BB is also valid. AA consists of even number of A's, and so on. Let us see some invalid strings. Okay, so these are some of the invalid string that belongs to the language. A consists of odd number of A, BA consists again odd number of A, and so on. One more example, strings that end in A. So this is how I can again define. This is another way how I can define a language. Okay, a language is made up of X. Language says X, and such that there exists Y, which is made up of alphabet set A and B. So Y is a string which is a combination of, which is any combination of A and B, such that X is equal to Y concatenated with A. So what does this say? X is the language. X is a valid string which is made up of concatenation of Y, which can be any combination of A and B, but it ends with, it is compulsorily concatenated with a character A at the end, right? So I can say string that ends in A. So these are the valid string, and these are some of the invalid string. Even epsilon is an invalid string because it doesn't contain any, it doesn't end with A, right? Okay. Few more example. Language that contains only epsilon. Okay. Um, if a language is defined in this way, W, which is made up of A and B, and the length of W is 0. So what is the only valid string according to the language? It's string of length 0, which is epsilon. So L consists of, L is equal to epsilon. The empty language. Okay. Here it's a special kind of language where the language itself is empty. You should have a very clear, you should make a very clear difference. You have to note the difference between the two. This language, which consists of epsilon, is entirely different from a language it doesn't contain anything. Okay, example, L is made up of a string from the alphabet set A, B, and my language says W should start with 1. So obviously I cannot start a string with 1 because W is made up of alphabet set A and B. So this language will have a empty set. Even a null string or empty string is not accepted. Or epsilon is not accepted, right? Okay. Functions on language. The set functions applied to the languages are, okay, let us take this particular example. If I take sigma as A and B, and these are the two language what I can define, L1 and L2. L1 says strings with even number of A's, and L2 says string with no B's. So the first function what I can apply is union, right? L1 union L2. So what would be the answer for this? So L1 union L2 is basically says both L1 and L2 is valid, isn't it? So I can have a string with even number of A's, that is from L1, or strings with no B's, and this is a valid example for L1 union L2, right? Epsilon B A AAB, etc. L1 intersection L2. So what can be the answer for this? L1 says strings with the even number of A's, L2 says strings with no B's. So I have to take the common factor from both these languages. So what can be that common factor? So the first one is there should be even number of A's, and L2 says there should be no B's. So I can have a string that is only even number of A's with the no B's, right? So this is the answer for intersection of L1 and L2. Okay, we'll continue. L2 minus L1. So this is the difference So it says strings that is present in L2 but not in L1. So what is the answer? Strings with no B's and odd number of A's, right? Negation of L1. So what can be the negation of L1? It's the exact opposite of the definition of the language L1. L1 says strings with even number of A's. So negation of L1 would be strings that doesn't contain even number of A, or in other words, strings with odd number of A's. Okay. Let us look one more example. Negation of L2 minus L1. So L2 minus N1 we have already defined. It's a string with no B's and odd number of A's. Its negation would be string with at least one B or strings with even number of A's. Concatenation. Concatenation of two languages. Here I have L1, which consists of cat, dog, mouse and bird. L2 is bone and food. So if I define or if I have to perform function of concatenation on L1 and L2, then I get L1 L2 is equal to cat bone, cat food. So each string from L1 is concatenated with each string from of L2. So this combination gives me the concatenation, and it is stored as a new set. And one more important point to be remembered, concatenation of a language is associative. So L1, L2 concatenated with L3 is equal to L1 concatenated with L2 and L3. The same is applicable with strings. Clean star. Okay, this is already told, but I will once again I'll repeat. The clean star is denoted by the special symbol star, okay, affixed to sigma. So this gives infinite set of all possible strings of all possible length over sigma, including epsilon. So any possible combination of the symbols alphabet set defined over sigma can be written by using star, okay, including no combination, so including epsilon. So epsilon gives zero combination of A and B. This is a lexicography enumeration of the given alphabet set. Starts with the epsilon, then one occurrence of alphabet set followed by two occurrences and so on. So this gives me an infinite possible combination of the sequence of symbols that can be constructed or that can be combined from the alphabet symbol, alphabet set sigma. Okay. Example, if L is equal to cat, dog and fish, then L star is epsilon, cat, dog, fish, cat, 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 dog, cat, fish and so on. So this goes up to infinity. Clean plus or clean closure, very similar to that of clean star, but with the slight difference. Clean plus is an infinite set of all possible strings of all possible lengths over sigma excluding epsilon. Okay, so only difference is this clean plus will exclude epsilon from the set. Okay, so string of length 0 is not present in as an answer to clean closure or clean plus. Yeah, same example but without epsilon. Language hierarchy. Okay, uh, so the language till now we were talking about the various properties of a language. Now let us see the various categories of a language which we will be learning in this course. For timing, we'll start with the simplest language, which is called as regular languages, and this is the hierarchy what is shown. See, the innermost the smallest level of or the simplest language is regular languages, and it can be built, the solution to which can be built by using FSM, which stands for finite state machines. Okay, and there are problems, there are languages to which I cannot have a solution using FSMs, and these are called as context free languages, which comes as a higher level language, right? So this FSM is restricted, so for only the solution for a given problem by using FSM is restricted only for regular languages. As I go outwards, then I require a different machines to solve the problems. So context-free languages can be solved using PDAs, which stands for push down automata. And still, there are non-context free languages which cannot be solved using PDA. These are decidable language and semi-decidable languages, which has to be solved only by using LBA or Turing machines. Okay, so Turing machine is the, I can say, it is the ultimate computing machine which can solve any given problem. Okay, so regular languages can be solved using FSM. And one more thing, the outer circle, the solution, the machines which is defined in the outer circle will be able to solve the problems which is present. I mean, which will be able to solve the languages which is present or which is represented in the inner circle. So PDA will not be able to solve only context-free languages. It will be able to solve regular languages also, but not non-context-free languages. So PDA can solve regular languages, context-free languages, but not decidable language and semi-decidable language, which is non-context-free language. Similarly, Turing machine will be able to solve all these kind of languages. So with the Turing machine, I can solve solution, or I can find a solution for any kind of languages. And in this, in the upcoming session, we will be looking only with regular languages. So in the upcoming session, we'll learn how to design an FSM and how to find a solution. Okay. So see you in the next one. Bye bye.